Welcome back, Nature in Code. We're in chapter 5 and we're visualizing a spatial simulation in JavaScript. And so we have to write this code. And I just open a new document here. And I'm going to start by declaring the doc type, as always, doc type, which is HTML. I'm going to add my HTML tag. And within the HTML element, I'll have a head and a body slash body. And because we're using the three the way we have before, I'm going to add the script tag here in the body. And I'm just going to go ahead and save this template here. And I need to create, obviously, a new folder because we're in a new chapter, chapter 5. And I'm going to name this Spatial Simulation. How about that? Spatial Simulation. All right. Good. So what do we need to do? Well, first of all, it's probably worth declaring a couple of variables that we might need down the road. So as I said, we're going to implement a two-dimensional grid. And implementing a two-dimensional grid means that, for starters, we will need to know how large that grid is. And so this is going to be a quadratic grid with, so the sides are going to be of equal length. And so I'm going to define that. Here's my first variable. I'm going to call that grid length. And let's say, this will be 100. So it's going to be 100 times 100. So we'll have 10,000 cells, 10,000 elements in this two-dimensional array, so 10,000 individuals. And of course, we can always change that later on if we want to. And we'll store the data in this array called grid. So I'm going to define this grid as an empty array. We will need to initialize the alleles. And I'm again going to do this at 0.5, so half of the alleles will be A1, the other half will be A2. What else do we need? Well, we have this mating distance, this maximum mating distance that I referred to as D in the previous video. So I'm going to call this max mating distance. And let's just set this to 1. So this is going to be the most constrained mating distance you can imagine. And then I want to keep track of the three different genotypes, and I'm just going to set up counters here: A1, 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 A2, and A2, A2. Of course, going to initialize those at 0. And finally, I will want to keep track of the number of generations we're running, so I'm just going to set up a generation counter here, and I'm going to initialize that at 0. That should be fine. All right, so what do we need to do first? Well, the first thing that we actually need to do is we need to initialize the grid. And how do we do that? Well, let's say we will call a function called initGrid. initGrid. And this function will initialize the grid. So let's go ahead and do this. Let's implement this function. Function initGrid. And then once we've done that, then we start implementing the generations that will be running and all the methods that all the functions that we need to call there and that we will need to define. But here at first, I want to initialize the grid. So let's go ahead and do that. This is going to be a two-dimensional array, so as you can imagine, I will have a nested loop. So I'm going to do exactly that. For var I equals 0, I smaller than grid length, and of course I equals I plus 1. And then the same thing again, nested loop, but I need be careful that you have here this new variable II, or J if you want to, but I'm going to use II as always with nested loops. So this is the second level of nesting, which is why I'm going to call it II. All right, so this is the nested for loop with which you would iterate over a two-dimensional array. However, at the moment, our array is actually just one-dimensional. It's in fact just an empty array. So what we need to do here is at the first level, we need to essentially push empty arrays into this array so that we have a two-dimensional array. So for example, grid.push, push an empty array. Now, push is quite convenient because you don't need to know exactly where you are in the array. You just push into the array, and you know the element that you're pushing into the array is going to be added at the end. And so that's usually quite convenient. However, as you are iterating with a for loop that gives you this handy counter here, you could also say grid I equals the empty array, because this would now just be the first element in the first iteration and the second element in the second iteration and so on. So you can really do this however you would like to do this. Okay. Now in here we can now access this this array, and specifically the II element of this array, which at the moment doesn't exist. So we have to initialize it to a certain value. And so this is essentially the cell. Grid III, that is the cell at the coordinates I on your grid. So we're going to use that throughout the development here of this JavaScript code. So what should this be? Well, we want to store an individual, but really when we speak of individuals here in this context, all we mean is genotype. So I'm just going to store the genotypes here in the cells. That is the entire representation of the individuals. So this should be a string, either A1A1 or A1A2 or A2A2. Now, which string should it be in this particular case? Well, we want to make sure we initialize this population at Hardy-Weinberg frequencies. And what does that mean initially? Well, if you recall the Hardy-Weinberg frequencies from the very early videos, they were given P. They were P square for the A1A1 genotype, 2PQ for the A1A2, and Q square for the A2A2 genotype. And of course, these added up to 1. So these are the Hardy-Weinberg frequencies given P, and given Q, obviously, which is just 1 minus P. Now, how do we implement this now in code? Well, there's an easy way to do this, and I'm just going to show this to you here real quick, because it's a good way to think about random events. Often when you have certain events that should happen with a certain probability and those probabilities add up, it's helpful to think of all the probabilities as like stacked on a line, on a number line, so to speak. So in this case, for example, we could say, okay, here we have a number line from 0 to 1. So we get all the numbers here, floating point numbers from 0 to 1. And now we could say, okay, so the first stack here is going to be up to P squared. And so this interval here represents the probability of having an A1 genotype. And then you could add the other genotypes here or here. It's perhaps now here easiest to think about, looking from the perspective here of 1. The interval here could be, A2. So what would this value be? Well, this should be the space of the length of Q square. right? Because q squared is exactly the probability of an A2. So on the number line here, this would be 1 minus q squared. And then the rest of the space here should be simply A1, A2. And the reason why this is helpful is because you can now think of math random, which generates a random number between 0 and 1, as, you know, sort of dropping a pen randomly somewhere on this line, and, you know, perhaps it lands here, and now, you know, because it lands here in this area, in this region, you should generate an A1, A2. And another time it might land here, in which case it would be an A1, A1 genotype, and another time it might land here again, would be A1, A2, another time it might land here, which would mean it's an A2, A2, and so on. So that's just a handy way to think of it. And so this is actually, you know, an idea like this is very easy now to implement in JavaScript code. Let's go ahead and do this. So here's our code. So rather than just setting a value here, I'm going to ask a few questions. First, I'm going to ask, well, first I'm going to sort of generate this random number, okay? Random number equals math random. Now this is the position on the line on which the pen will come down. So now I just have to figure out where exactly that it was. So was it somewhere in the area where the value was smaller than p squared, p times p? If so, we should initialize this as, so the grid I should be initialized as A1, A1. Yeah. Now, what was the second thing that we were asking? Well, we were asking, else, if that's not the case, then perhaps it is the case that the random number falls, random number falls somewhere here. Let me go back to the slide. In this space. We can also first ask, well, does it land on this space here? So when does it land on this space? Well, it simply lands on this space if the number was larger than 1 minus q squared. So we can ask this question. So if the random number was larger than 1 minus q times q, and I realize I haven't defined q yet, but stick with me for a second. In this case, we would have, grid I, we would have an A2 genotype. So we don't know what Q is, but we actually do. We just haven't defined it yet. And let's not define it. Let's just say, well, let's just replace this with 1 minus P. Okay. And I have to put this here in parentheses so that this will be calculated first. And finally, if that isn't true either, then it must mean that we're in this intermediary space where we would initialize the element to the A1, A2 genotype. And that's pretty much it. So the only thing that we want to do as well is, because we're keeping track here of the genotypes, in the case we assign an A1, A1, we should increase this A1, A1 counter by 1. Correspondingly down here, we should increase the A2, A2 counter by 1. And finally, of course, if it's a heterozygote, we should increase the A1, A2 counter by 1. So if this worked, then we should now have initialized a grid with Hardy-Weinberg genotype frequencies. Of course, this is going to be some sort of an approximation. The numbers will not be exactly Hardy-Weinberg because, well, we're still working with finite population sizes here, but given 10,000 individuals, this should be fairly close. So let's just go ahead here and output the number once we have finished this loop. And if you have done the indentation nicely, as I have here, you will immediately see that this here is the curly bracket that closes this bracket here. So after that, I'm just going to say console log A1, 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 A2, and A2, A2, just to see whether that actually worked. So let's go ahead and save this, and let's go over to Chrome in my case, or your browser of choice. Open file, chapter 5, spatial simulation. We're going to open this. We're not seeing anything here yet, but we're printing into the console. So let's take a look here at the console. Here it is, and this looks pretty good, right? Because p is 0.5, so p squared is 0.25. 25% of 10,000, yeah, that's approximately correct here. Same here, this is 2pq, which is 0.5, and this means about 5,000 individuals, and again about 2,500 individuals for the last genotype A2A2. And if I reload this a couple of times, we'll see that's always approximately correct. All right, so we have successfully initiated this grid, and in the next video we will now start running the generations. So I'll see you in the next video.